Welcome to the dimensional analysis module. This module it has two lessons. The first lesson is review of dimensional analysis, things you have done before in fluid mechanics, for example. And the second lesson, pi theorem, we will see that the dimensional analysis that we do intuitively, actually there is a rule for it. And if you followed this rule, you could approach more complex problems, and these have application particularly in physical modeling. So we will learn the pi theorem and physical modeling. So let's just get started with the dimensional analysis review. So that would be like lesson one, part one, dimensions and unit. So So here, that is like lesson one, part one of lesson one, the dimensional analysis review, dimensions and unit. So the objective of this lesson is to review the concept of dimension, what's dimension and what are their corresponding units, and then do some practice for uh, primarily, like practice primary and non-primary dimension and their associated like SI units mainly. Okay, so these are the two objectives of this lesson. Let's get started. So what is dimensions and units, and what is the difference between dimensions and unit? So as an engineer or like a scientist, fundamentally what we are doing is that we are measuring physical quantity. We are measuring these physical quantity either to understand or design like a system. Yeah. And what we are measuring uh, is called like a dimension, like a measure of a physical quantity. That is called a dimension. Yeah. And a dimension is just a measure of physical quantity without a numerical value. So what are things that we measure? Like, can you just like pause the video and just think in physics, what are the things that we measure? Primary dimensions, yeah. Okay. So one thing we measure, for example, is distance. Yeah. So we could measure distance in 1D. That would be like a length. We could measure distance in 2D. That would be an area. That could be an area. We could measure distance in 3D. That could be volume. What else do we measure? We measure time. Yeah. That's another thing we measure. What what else do we measure? Uh, we measure mass, like the mass of a substance. So that's like a third thing we measure. Uh, so these, what I just mentioned now, these are called like primarily dimensions. Non-primarily dimension are things that we measure that are derived from this primarily dimension. So for example, we measure velocity, that is distance over time. So we measure acceleration, that is velocity over time. Okay, so these are example of non-primary dimensions. A unit is just a way to assign a number to a dimension. So for example, uh, we could measure this length here, and we could measure this length, and we want to assign a unit for this. We can assign a meter. Actually, this is a historic meter. So, and this is how like a meter is defined. If you're curious what like how to define a meter. But you could also measure the same length with feet. Yeah. So basically, that is the unit that you add to a dimension. So there are physics primary dimension or like these are called like fundamental or basic dimensions. That's like everything in physics, anything you're doing in physics, as I will show you now, it could just be reduced to 7 things. Yeah, these 7 primarily dimensions, and these 7 primarily dimensions are like length, like that's in meter, for example. That's the unit would be in meter, or English unit would be in like foot. Mass, English unit would be in kilogram. Sorry, SI unit would be in kilogram, and English unit would be like slug or pound mass. Time, SI units that would be second, English units that would be second. Temperature, Kelvin, uh, and then so these basically like as civil and environmental engineer, basically these anything we are doing, anything you are measuring will be reduced actually to these 4 things. And actually this one also, the amount of matter, so that we measure this in mole, like the amount of matter. Additionally, like if you are an electrical engineer, you might be measuring additional things like electric current. Civil engineer also like water resources engineering, like electric current. For example, if you're doing some geophysics, hydrogeophysics, then that would be important. Also, you'll be measuring like electric currents as well. And then finally, like the last thing is the amount of light. Okay, so basically anything in physics could be reduced to these 7. And I will show you now. So all non-primarily dimension are formed by combination of these 7 primarily dimension. And here I I made this for you. Bring it here. I made this for you, which have like this fundamental and derived physical quantities that are commonly used like in fluid mechanics. So I prepared like this table for you, and I will show you, for example, like how to derive all these guys now, like from primarily dimension, like length, time, and mass, how you could drive all these other guys. Yeah. So like the link of this one is here and it's also in the video description. So let's look at the velocity, for example. Yeah. So velocity. So what is velocity? So velocity, that would be distance over time. Yeah. So what would be the dimension of this guy? So distance, that is like length. Time, that's like t. And then so the velocity will have like the dimension of L over t. So that would be like, oops, that would be like the dimension of this guy. Acceleration, for example, that's the rate of a change of velocity. So acceleration, that would be like velocity over time. So velocity over time, so that is the unit of velocity over time. So basically that would be like L over t squared. So that would be uh, the dimension of like acceleration, like L length over t squared. Force, so like force, that is like mass time acceleration. Yeah, so mass. So what would be the dimension of force? So the dimension of force, that would be mass. That's like m over acceleration. That's like L over t squared, for example. Yeah. Weight, that is like mg. Same like mass time acceleration due to gravity. So that would be the same m L like t minus 2. Same as this guy here. Density, uh, volumetric mass density. So density is like rho is equal to mass over volume. So what is the dimension of this guy? So mass, that's like mass, and volume, that is like L length cube. So the dimension of this guy is like mass and like L cube. Specific weight. So specific weight, that's like giving by gamma like is equal to rho g. And the specific weight. So again, what would be the dimension of like specific weight? So we know that this guy is as this is L minus 3 here, because this is mass over volume. Yeah. So we know that this guy, that is like the dimension of this guy is like m L minus 3. And the g, we know that the dimension of this guy is like L over t minus 2. Yeah. Length over time square. So what do we get here? So like from this guy, that would be equal to m L square minus like t minus 2. So that like specific weight, that would be like the dimension of specific weight. Yeah. Specific gravity. So specific gravity, what is the specific gravity? That is the ratio of the density of a substance to the reference density, which is like usually water. So like usually like specific gravity, we generally write it like this. So that would be like the density over like the reference density, which is like the density of like reference whatever that is, like usually water. So that's like specific gravity. And so basically that is like density over density. So that is like this guy here over like this guy, and that will give you like 1, which is like basically dimensionless. That would be dimensionless. Okay. Surface tension. You remember like surface tension? So surface tension, that is like force. Surface tension, that is force. So surface tension is usually surface tension. That's like force over length. Yeah. So that is surface tension is like force over length. So what is force? So remember, like force, that is like mass time acceleration. So acceleration, that is like L t minus 2, L over time square, and like length, that is like L. So surface tension, that would be like m t minus 2. Yeah. So that would be the surface tension. Yeah. What would be like the unit of this? Like remember, like here, I mean, I forgot to tell you this. That's important. The force. What is like the unit of the force? So the unit of the force, it could have like a different unit. So like here, for example, I could give it like kilogram per meter per second square. Yeah, delete this. Per second square. Kilogram meter per second square. That's like the unit of the force, because m is kilogram. That's like SI, like in and like length, that's a meter, and times that's a second square, which is like an SI unit. We refer to this as like Newton. Yeah, so the force is like Newton. Okay. Same here. That would be like in Newton, in SI unit. Yeah. So surface tension, kilogram per second square, or like a Newton meter. Yeah. So let's look at pressure. So pressure usually is given by either capital P or small p. So pressure, that's like force over area. So what is the dimension of this? So the dimension of this, like force, is like mlt minus 2, for example, over area. That's like L square. So that will give us like ml minus 1 t minus 2. Uh, what would be the unit of this guy? So the unit of this guy, that could be like Newton per meter square. Yeah, that's like usually giving like a Newton per meter square, or you can give it like kilogram per meter per like second square. But it's usually like giving a Newton per meter square. Another important thing like energy, work or energy. So let's say like energy. So energy usually energy. And energy, that's like force time distance. So again, that would be like ml. So like what would be the unit of this guy? That would be m force. So that's like ml t minus 2 time like distance l. So that will give m l square t minus 2. That would be like the dimension of energy. Or in again, like the SI unit for this, that would be like you can say like it's Newton meter. But in SI units, this also has a different name other than Newton meter, which is joule. Okay, so Newton meter, SI unit, that's equivalent to like joule. Okay, so that's equivalent to joule. Okay. Uh, momentum is a momentum. Uh, momentum, that's usually like mass time velocity, for example, and you can give it units, so that will have like m, and velocity that's lt minus 1. It's mass time velocity. Yeah. We have power. So power, basically, that's the rate of like doing energy. So power, usually, that's like energy over time. It's like usually giving it energy over time. Or remember, like energy is force time distance, so it could be like also force, which is also force time velocity. Yeah, because distance over time that gives you velocity. And uh, the same here, like the same here, uh, like you can say like you can give it like a unit of like joule per second, for example. That would be the unit, because like, the unit of energy is joule and time is second. Or you can give it a unit of like Newton meter per second, because that's like the force in Newton, and velocity is just like a meter per second. Or you can, in SI units, the unit of power is actually uh, not like joule per second or Newton meter per second, it's actually watt. Yeah. And what would be the dimension of this guy? Like if I ask it, can you tell me the dimension of power? Well, you know how to do this. So the dimension of power, that's like force. So that we know like force, that is like m l t minus 2 time velocity, that is like l t minus 1. So that will give me m kilogram meter square per second. Kilogram meter square per second cube, which is watt, which is Newton per meter per second, which is joule per second. Yeah. Okay. Uh, one more thing before we finish this part, like let's do viscosity, dynamic viscosity. So that would be like the first one, and then so viscosity is generally given by mu, and viscosity, that is like shear stress. So that would be like the shear stress over uh, uh, it's called like is shear velocity basically. So that is like delta V over delta Y. That's it's called like shear velocity or yeah. So shear stress again, like what is the shear stress? So the shear stress, that's like pressure, like similar to pressure, that's like force over area. So here like we have this guy, that's like force over area, and this guy that's like velocity over delta V over delta Y, that's like a distance. Yeah, so we can just say here like delta Y here, we can put like the delta V here. So if we want to find like the dimension of this guy, so that is like force. So what is force? Remember force, that's like mass, LT minus 2. Delta Y, that is would be L over area, that's like L square, and delta V, that is like LT minus 1. So if we did this guy, uh, so this guy will go with this guy. Uh, this guy will go with this guy. So here I have minus 1. So basically, I will end up with something like M L minus 1 and like T minus 1. So that would be like the dimension of the dynamic viscosity. Yeah. Uh, and dynamic viscosity is like if you can like it's usually like giving like you see here this is like force over like if this guy goes this guy that will give you a length, so it is usually this is like Newton, yeah, and that would be like here that length would be like a meter, and V that is like meter, and that would be like per second, so you can put like the second here. So it would be generally given as Newton per second per meter like square. That's like that would be the unit of this guy, or simply like what we, or you can just simply like what we generally do, like we give it the unit from this guy. So from this guy here we have like M, that's like kilogram, and length that would be like over uh, length that's like meter over second. So you can have like so basically like these two are equivalent. Yeah, Newton per second per meter square, kilogram meter per second. Okay. So basically, this is just some dimensional analysis. But why this is important? Like why? I mean, why this is important? So let me show you just like one application, like one quick application for this. Remember, I told you in this lesson we will like we are doing these things intuitively. Next lesson, we will see a rule, systematic way for doing this, which is like the pi theorem, and you can do like more advanced application. But for now, let's do a very simple application, like not anything advanced to show you like how dimensional analysis could be useful. So here, dimensional analysis can inform you about the dimension of a proportionality constant. So what you see, like in this figure, this is Darcy experiment. So Darcy, he's a French engineer. He made a very important contribution to the area of hydrology and hydraulics. So Darcy law, for example, that's the basic law for groundwater flow, from which you can get the groundwater flow equation. You have Darcy-Weisbach for channel and pipe flow, open a channel flow and pipe flow. You have like Darcy-Weisbach equation. Uh, and what he did, like he wanted to study flow in porous media. So let me explain what you see here. Okay. So basically, this is a sand column. So you have like some screens here, and this is sand. And you have like water will be flow from here to here. Why? Because this is like high energy. So energy is expressed as in terms of hydraulic head. Uh, and you have like low energy here because you have a low head. So here you have a high head and here you have a low head. And generally what nature like to do, like nature does not like this. What nature likes is that it likes to reach an equilibrium. So it does not like to have a high energy here and low energy here. It likes the energy here to be equal to the energy here. And due to this gradient in energy, the water will be pushed and you will have a water, like the flow of water, like water will be flowing from here to here because from high energy to low energy. So Darcy wanted to understand the flow in this column, like he wanted to find a physical law that describe flow in a sand column or in a porous media. Okay. So let me ask you a question. What do you think this flow, like Q, so flow here, like this charge Q, like here, what is, so this is charge Q, and remember like Q, that is, that's like volume over time. So what is the dimension of this Q? So we know like volume, that's like L cube over time. Yeah, so that's like the dimension of flow. So this Q, what factor do you think this Q would be like a factor of? So we know that like so Darcy, like you were asked to do an experiment, like you want to see Q, like how Q in porous media very different on which factor, like what are the important factor and what are not like the important factor. So one important factor for sure would be like the H, because if H here is equal to H here, there will be no flow. If H here is much higher than H here, like you have much more higher energy gradient, then you will have high flow. So Q is proportional to H. So this sign here, like if you don't know what this is means like a proportionality sign, which means that like as H go, as, let me write it the other way, like as H go up, Q will go up. Okay, so as you have more energy gradient, then you will have more flow. Yeah, so that's like one thing. What would be the other factor? The other factor would be like the distance, like this column length here. Yeah, so that would be like the distance. So the larger the smaller the distance, the more you will get Q. Yeah, and the larger this distance, the less you will get Q. And this makes sense because as if you have like a large distance, remember like as water flow in this sand column, energy will be lost from the water because there like some of the useful uh, mechanical energy will be converted to heat energy. So the longer this sand column, the more you lose energy, the less Q you will have. Yeah. Uh, so basically, Q would be inversely proportional to L, like to the length, like here, this L here. Okay. What are the other factor uh, that will like control like this Q? The other factor would be like this area actually, like this surface area here. So like if this is large, like if you have a big area, then you can pass more Q. If this is a small, like you have a small area, you will have like less Q. So basically Q is proportional to like the area. Yeah, so if you have like high area, you'll have high Q. If you have high length, you'll have less Q. So this is called directly proportional. This one to one, like if this go up, this will go up. This is called like inversely proportional. If this go up, this will go down. Yeah. So basically, we can write an equation for this. Yeah. So basically, the equation for this would be like Q is proportional to, yeah, it's proportional to H is inversely proportional to L and is directly uh, less, yeah, is inversely proportional to L and directly proportional to A. Yeah, it's L here. L. So A is directly proportional, Q is directly proportional to A, H, and L. So now dimensional analysis could be very helpful because here, if we want to remove this proportionality sign and put an equal sign, we can do this. Yeah, so I can say like Q. Oops. I can do this like I can say like Q is equal to, I'll put like this constant, like is equal to Q A H over L. Oops. Q A H over L. So now I got rid of this like proportionality sign by putting this constant. So this is just a constant, yeah, to remove this and make it equal. So now the dimensional analysis could be very useful because it could tell us like this unknown constant, like when Darcy did this experiment, this constant was unknown for him. He can know the unit of this constant. Can we know the unit of this constant? Yes, because we know the unit of Q. So Q has the unit of M mass, sorry, Q that's volume over time. So that's like L cube over time. This proportionality constant, we don't know this guy. Let me just get rid of this. We don't know this guy. We know the A, that's like L square. We know H, that is like hydraulic head, that's in length. So the hydraulic head is measured like in length, meter or feet or whatever. And then we know the length, like this length here, and this is given as also L. Yeah. So then what will be the unit of this K, of this proportionality constant? So let's see here. So here have LT is equal to L square. So what would be the unit of K? So that makes the unit of K is equal to L over T. That would be like the unit of this guy. Yeah. And this guy is term is like this K, which has like the unit of L T minus 1. This is called like hydraulic conductivity. So this guy is hydraulic conductivity and it is a function of both is porous media property, like this is sand, clay, whatever. So if this is, for example, like gravel, that has very high hydraulic conductivity, water can flow easily. If this is clay, very low hydraulic conductivity, water will not flow easily. And also it is a function of the fluid. If it is honey versus water, for example, yeah. So this hydraulic conductivity, it's a function of both the fluid, like the fluid viscosity, density, so on, and it's a function of the porous material, like sand, clay, or whatever. Okay. So you see this exercise, we just like use dimensional analysis. Like if you are Darcy and you're preparing this experiment, you will you can just use dimensional analysis to know the unit of this proportionality constant here. Okay, so now This is like a practice problem, so I'm not gonna solve this problem here. This will be for you to do more practice at home. So what you can do, you can just like pause this video and try to solve this one. And the solution is actually in the lecture notes. So if you go to the Canvas, on this module, like in the lecture note, you will find the solution. So here, for example, so that is the solution of this one. But don't look at the solution. Try to solve it on your own and then like check the solution. So in this practice problem, this is hydraulic conductivity. Remember, we talked about this before. This has a unit of L over T. Yeah. And I'm telling you what is the unit of this guy here. This is like this called permeability, like this small guy here. It's called like this called hydraulic conductivity, this called permeability. Again, if you don't understand the physics, if you don't understand these terms, doesn't matter. That's the whole beauty of dimensional analysis. You it's like more like math. Yeah, you don't need really to understand this. You just try to get the dimensions correctly. Yeah. So here, this is permeability. This is a specific weight per unit volume. Like remember we did this specific weight, and this is dynamic viscosity. So you know the dimension of this guy. You can drive or like check the dimension of this guy from any table and then find the dimension of this guy. So try to find the dimension of this guy. Like L, is it L square, L over T, whatever. Yeah. So and check your answer. Yeah. Here, this is the link where I mean, you know how to do this. Yeah, we did this already before. You know, like how to find the dimension of like specific weight. You know how to find the dimension of viscosity. We did this, and you know the dimension of this guy. Yeah, then you can find the dimension of this guy here. Okay, and then homework problem. So if you already understood what we did here, this is a homework problem again. You can solve it now and then you can submit your answer to Canvas. Okay, so basically very straightforward. Again, like the learning objective is to ability to apply fundamental principle, because what we covered in this lesson, these are fundamental principle in any engineering analysis. This is not advanced engineering analysis, but this is a fundamental principle in engineering analysis. Yeah. Okay. So I think that is conclude this lesson. In part two, next lesson, I will show you. I will talk more about like what we did here. Actually, what we did here, this is called dimensional homogeneity. So dimensional homogeneity means that the dimension in the right hand side is equal to the dimension on the left hand side. So for any physical equation, physics based equation, not empirical equation. Empirical equation, you don't need to maintain dimensional homogeneity, but any physics based equation, you need to maintain dimensional homogeneity. What does dimensional homogeneity mean? Means that uh, the left hand side, the dimension of the left hand side should be equal to the dimension of like the right hand side. So here, for example, the dimension of the left hand side. So let's look at this like Q is equal to K A delta H over delta L. Yeah. So we know so the dimension of this guy Q, we know that Q, that's like L cube over T. Yeah. So that is equal to K. So K we know that's L over T. And A, that's like L square. And here like delta H over L, that's L over L. Yeah. So if you check, is this equation, does it has dimensional homogeneity? Yes, it does. It has dimensional homogeneity. Why? Because on the left hand side we have L over T, and on the right hand side we have L cube over T. Yeah. L cube over T, L cube over T. So you have dimensional homogeneity. Okay. But that's next lesson. So I'm just like giving